Hey, welcome back. In this video, we're going to review the concept of parametric equations and how to sketch parametric curves. We're also going to tackle the idea of eliminating the parameter to create a Cartesian or rectangular coordinate equation given your parametric equations. We'll also detail the idea of the flow of the parametric curve or the direction of the parametric curve and issues with when in rectangular coordinate form, how to find the domain. First things first, a quick review of the concept of parametric equations. What you'll be given, as in this first example, is an equation in terms of a third variable that defines x and y. Y in this case is called the parameter of these parametric equations, and the final graph that we're going to have is called a parametric curve. Importantly is that parametric curves are slightly different than normal curves we have in the Cartesian plane because they have a direction or a flow to them that's described by the parameter. In this example here, we're being asked to sketch this parametric curve, and one thing we could do is eliminate the parameter first, but one easy way to attack any of these sketching of these parametric curves is simply by finding points. So what I'm first going to do is I'm going to iterate this parameter from -2 to 2. I'm just going to focus on the integers when I do this. Obviously, this is actually a continuously defined function for all the values between -2 and 2, but the idea is if I can see the path and the journey from getting from point to point, I can easily sketch this curve. So in order to find my ordered pairs to plot on a graph, all I'm going to do again is select these integer values from my parameter and plug them in each of these equations. What I'm going to do first is get values for x, then values for y. These pairs of x and y's become my ordered pair points that I'll plot on the graph related to their parameter value. So when I plug -2 in for t, for this x value right here, I'll get -2 to the third is -8. -8 times 2 is -16. -16, and then this will become a plus 10 from the -2. So -16 plus 10 gives me a -6. And I won't walk through all these. It's just simply plugging these in and evaluating each of these. But I did this just a second ago, and these are the values that I got for my x. And then I do exactly the same thing for my y values, plug in a -2 here. This first one would give me a -8 minus 2, which is 10. And actually in this case, since I'm going up by ones here, I actually can just use this slope here to write the rest of these. For every integer value I increase, this goes up by 4. So sorry, that was -10. This is going to be -6, -2, 2, and 6. So then I have these ordered pairs described by the parameters. What I'm going to do now is plot those. One thing importantly as I plot these, I'm actually going to label each of these with their parameter value, and you'll see the reasoning for this for 1 second. But let me just show you this first one real fast. So this is x equals -6, y equals -10. That point is about right here. And that's the value when t equals -2, and then 3, 6, so 3 and then -6 right here. This is when t equals -1. When t is equal to 0, I'm at 0, -2, so I'm right there, and that was t equal to 0. For t equal to 1, I'm at -3, 2, so -3 and 2, that's about right there. That's when t equals 1. Finishing up with when t equals 2, I'm at 6, 6. And so that will be somewhere right there. So using this method, all I'm going to get then are these discrete points. I kind of think of this as remember when you were a kid and you used to connect the lines, connect the dots, right? To make like little animals or things like that. That's all I'm going to do. One thing that you can do when connecting the dots, outside of eliminating the parameter to look at the Cartesian version of the equation, is to simply look at the kind of curves that you have describing your variables. This can sometimes get more complex and hard, but importantly in this case, I see this linear for y and then this cubic for t or for x here. And when I'm looking at this journey, this kind of looks like a sideways cubic. And so I'm just going to use that logic when I'm doing this to try to have a graph that is somewhat of the same nature of what I have here. So my journey starts right here at t equals -2, and then I'm just going to journey through these points in this right here. And then importantly to this conversation is the fact that this graph importantly has direction. It starts here at -2 and then ends at 2 right there. And so we'll often throw in these arrows, which describes the flow or the path of this parametric curve. A really useful way of thinking about this is thinking about this parameter t being this variable of time, and then as time goes on from t equals -2 to 2, this is the path of this object on this two-dimensional plane. One useful way of analyzing the parametric curve for parametric equations is to go straight ahead and eliminate the parameter. When eliminating the parameter, what we're looking to do is instead of have these two equations that describe x and y in terms of t, what we want is a curve that is an equation for the curve that is in terms of just x and y. Before I get started with this work, one thing that's really important when we do this is that the parametric equations always come with a domain for the parameter, which defines not just the flow of the graph, which will be important for sure, but also describes the domain. So looking at this equation right here, it's important to be able to realize that in this case, what are the range of the x values and the y values? As we can see on the graph and from our table, it's pretty straightforward right here. But in this case right here, the x values will vary from -6 to 6. Also look in this table from -6 to 6. And then the y values go from -10 up to 6. Why that's important is that when we create this equation, we need to then describe, we're going to have an equation in terms of two variables that could be valid for all real numbers of x and y. But what we need to do to actually efficiently describe this curve is limit it by some kind of domain restriction if necessary. First things first, what I always do is I'm going to rewrite those parametric equations over there without that function notation. Just makes the life a little bit easier and a little bit more obvious what I'm trying to do. So here is x and here is y. What I then am going to do is simply take one of these equations in this case, and I'm going to solve it for t. Once I get that value of t, I'm then going to plug it into the other equation. Therefore, I've eliminated the t by substituting an equivalent expression in terms of x or y. Besides straightforward substitution in algebra, there's a couple of other tricks that we use to eliminate the parameter. In this case right here, though, what I'm going to choose to do is I'm going to solve this second equation for t so t in terms of y, and then I'm going to replace t in this equation with an expression that has y in it that's equivalent to t. The reason I'm working with this equation first is the fact that the x equation is really difficult to solve for x. Generally speaking, my attack is to take the x equation and solve it for t and then plug it in to the y equation. And the reason for that is then I'll have an equation y equals some jazz with an x. And that makes it a lot easier to analyze what the graph is, since most of our understanding of graphical representations of equations and functions are in terms of y equals. But in this case, I really can't do that. And actually, if you look at the graphical representation, I would know that this is not going to work out nicely as a function of y in terms of x, because in this case, this does not pass the vertical line test, right? If I was going to get y equals some nice function in terms of x, this would have to pass the vertical line test. But actually, if I look at it from the other direction, it passes a horizontal line test, which means this can be a function of x in terms of y. But that's a lot of extra details. So what I'm going to do first, I'm going to take this equation right here and solve this for t. So I'm going to add 2 to both sides and then divide by 4. I'm sure you can see that. I'll do that pretty quick. But I'll get y plus 2 divided by 4. Then what I'm going to do is take that value of t and plug it in here and here for this first equation. And that will give me x equals 2 times t, which is y plus 2 over 4 cubed, minus 5 times t, which is y plus 2 over 4. At this point, I now have eliminated the parameter because I have an equation in terms of x and y. I could expand this. That would be x plus 2 cubed, which is going to get a big, long expression. I'm not sure how much that would help. But what I will do are pull out these constants. This is 4 to the third, which is 64. If I pull out that 64, I get 2 over 64 is x equals 1 over 32 here. And then I'll just leave this in parentheses. And the same thing here, take this minus, it'd be now 5/4 times y plus 2. So there I've done the work of eliminating the parameter. The only important thing to say is that this graph right here, if I graphed it, would look exactly like this, but these would go on forever in negative and positive infinity. Again, looking like this cubic that's kind of laid on its side, because it's a cubic it's an x function that's a cubic in terms of y, which gives it this sideways action. But importantly, what I need to do to describe this shape right here that I see is to use this parameter and readjust it with my new domain. Now, in this case, my domain is described by my independent variable in this case, which is y. And so as we can see from the graph right here or from this table of values, my new domain for this function is that y goes from negative 10 up to 6. All right, so in this example here, we're being asked to eliminate the parameter and to sketch this parametric curve. And in that case, what I'm going to get is a Cartesian. When I eliminate the parameter here, I'm going to get a Cartesian or rectangular coordinate equation relating x and y, again without the t. The one thing that I'm going to do in this case first is I'm going to list the range of values for both x and y just to get an idea. So from t goes from 0 to 2 pi. In this first one here for the x values, I know cosine itself, as I go from 0 to 2 pi, outranges values from negative 1 to 1. But in this case, since I have this amplitude of 2, x will actually go from negative 2 to 2. And then the same argument for y here from 0 to 2 pi. Sine outputs the range from negative 1 to 1. So the values I'll get out for y are from negative 5 to 5. So the next thing I'm going to do is eliminate the parameter. This is awkward in this case, and this is important because what I could do is, for instance, for the x or the y, usually I would look at the x first. So I would solve this for x, but that's going to involve invoking the cosine inverse function. And things get a little hairy at that point because the cosine inverse function has a very restricted domain and range of values. What I can do instead, so I don't lose the information that would be lost in using the inverse function, is actually use a trig identity. So what I'm actually going to do here is I'm going to take these equations and I'm first going to solve them for cosine and sine. So for in this case right here, I would get x over 2 equals the cosine of t. And in this second equation, what I'd get is y over 5 equals sine of t. So then what I'm going to use, since I have sine and cosine in this case, I'm going to use the Pythagorean identity that sine squared of t plus cosine squared of t must equal 1. So then in this case right here, I'll simply replace for sine of t this y over 5, and for cosine of t is the x over 2. And so this becomes y over 5 squared plus x over 2 squared equals 1. Clean things up, I like writing the x term first here, so I'll write this as x squared over 4 plus y squared over 25 equals 1. So there I've eliminated the parameter. Now the question becomes, what is this shape right here? And you may realize that this actually is an ellipse. So this is the equation for an ellipse. And this equation has the characteristics that the major axis will be on the y-axis going from negative 5 to 5, and on the x-axis from negative 2 to 2. The analysis here is, first of all, it's an ellipse because these are added, these are both squared, and so the range of values on x and y are determined by the square roots of these numbers being divided. Give me a second and I'll start to sketch this out. So again, this ellipse here will be this circular shape that has a major axis that runs along the y-axis. We call this the major axis because it's the longest of these two axes. In this case then, this will look something like this. which ended up coming out pretty nice. That's pretty good. Quick checks here real fast. Just on these statements, you'll see our x's varied from -2 to 2, which is what the x values, all the x values on this ellipse do range from -2 to 2. And I see I don't have my negative right here. So let's write this as a -2, rewrite this as a 2 so I can see it. And then my y values go from -5 to 5 as described. The only question I have then is the flow of this. Like, so where does it start and where does it end between 0 and 2 pi? And you might have some intuition of this because of how the unit circle goes as you increase your angle from 0 to 2 pi. But it's just a quick analysis right here. When t is 0, so we're starting at t equals 0 right here, and I plug in a 0 for t in both of these cases. The cosine of 0 is 1, so x is going to be 2 when t is 0, and when t is 0, sine is 0, so y is 0. So when the t is 0, I get x equals 2 and y equals 0, which gives me this point right here. So this point gives me when t equals 0. And then I don't need to go through all of the values, but just check one more known value. Let's go up to pi over 2. My intuition is it take me up to this point right at the top of the unit circle, but let's just double check real fast. At pi over 2, when I plug in pi over 2 here, cosine of pi over 2 is 0, so my x value will be 0. And at pi over 2, my sine is 1, so my y value will be 5. So actually, this is the point right here when t equals pi over 2. And then importantly, you can see what's going on here. I'm starting at t equals 0. I could have tested more points in here, but I'm getting the idea that this parametric curve starts here at 2, 0, is flowing this way around. And so in this example, we're being asked the same thing. To eliminate the parameter, create a Cartesian equation of this relationship between x and y right here, and also sketch the parametric curve. In this case right here, I have these exponential functions. One thing that I could do, just to say, I'm doing it a little bit differently, but just to give this, to be clear about this, again, I like attacking this each, see if I can make this y a function of x by taking this. And what I could do is apply the natural log to both sides to get the natural log of x equals t, and then plug that in for t right here. And actually, that would work just fine. I'm going to attack this a little bit differently, but actually before I go about doing the elimination, I just want to do this quick check again about the x and y values. This is always nice to do in the beginning so that I don't make a mistake with my domains or my final sketch of my graph. So in this case, when t starts at 0, my x value becomes 1 because e to the 0 is 1. So x starts at 1. And then as t increases without bound, in this case, x also increases without bound. And so in this case, x will always just be greater than or equal to 1. There's no upper bound for this curve right here. And the same thing when I look at this. If I plug in t equals 0 into this, I'll get e to the 0 is 1. So y, the minimum value at t equals 0 for this function is 2 because 1 plus 1. So I have 2 is greater than or equal to y, or y is greater than or equal to 2. And actually in this case also, there is no upper bound because t is not bounded. This will increase. One interesting thing about when I'm analyzing this, I know that these are the lower values for when t is 0 because these are both increasing functions. As t increases, these values will also increase. So these t equals 0s are these lower bounds for the value of x and y. So now let's talk about eliminating the parameter. And again, as I had said, I could apply the natural log to both sides of this and plug that in. That actually works just fine. I'd end up with exactly the same solution that I would get in this case. But I want to just have you see this trick right here because you might find a use for it moving forward when you have more complicated parametric equations. In this case right here, so I have x equals e of t, and I can kind of see e of t here. In fact, what I'm going to do is I'm going to rewrite this as, instead of e to the 2t, I'm going to write this as e to the t squared, which is an equivalent statement of e to the 2t. Because I'm raising this exponential expression to a power, I would multiply these exponents together. But then now what I can do, I have e to the t equals x. And so actually really quickly what I can do is replace e to the t with x to get that y equals x squared plus 1. So then after finishing that work right there, I realize that this parametric curve will have the shape of a parabola. Importantly at this point though is I analyze my domain, and in this case, since this is it's y in terms of x here, this function, I can just think about my domain restriction here where x is greater than 1. And so I'll write that here real fast is that my domain, and I'll write it in interval notation, is x is greater than or equal to 1, so it's from 1 to infinity. So then to go to sketch this, I know that this figure is a parabola. It's actually just a non-stretched horizontally or vertically x squared parabola, just shifted up 1. And so it will look something like this right here. And I've importantly used a dotted line for that because I know that I'm not going to use that entire curve. I'm restricted by this domain of 1 to infinity. So let's say 1 is right here. This point right here is 1, 2 on this graph. And again, I know the range for y goes from 2 to infinity and x is from 1 to infinity. And so this curve will look like this. And importantly right there, when I put the arrow, I kind of made note of it. But the fact is this parametric curve does go this way. It increases from left to right. And there's different ways of reasoning that. Part of my reasoning I was just talking about is that as t increases, both x and y increase. They increase in this direction right here. I could plug in t equals 0. That's actually where I got the 1 and the 2, saying that it starts right here at t equals 0. I could do a couple more test points just to make sure it's going this way, but to me it's pretty obvious that it's going that way. So that is my parametric curve with the flow provided right there, the direction of the curve. And importantly, just to say again, this dotted line I'd put in was just to give me a framework for which to work, but this dotted line does not appear in the parametric curve. It's just this part of the graph right here. Then in this last example, what we're going to do just show is this idea of parameterizing a curve. There are different reasons for doing this. Again, we know that we have these rectangular or Cartesian functions. They don't have a flow or a direction to them, but by parameterizing or giving them a parameter, we actually can create a flow given a specific situation. And again, this might feel just like a cool math trick that we're doing. There's actually real applicable reasons to do this. But generally the basis is this. There's one way to do this. There's actually an infinite number of ways to parameterize this curve. When you actually do this, you'll probably have different reasons for a specific type of parameterization that you're trying to use. But the simplest in this case would be to describe x, that the function x of t is just t. So in this case, you say, well, x is defined by t as just being t right there. So you're basically doing a substitution for t in this situation, and then you can say that y of t equals 2t squared minus 5. And if we were given a domain restriction here, we'd have to realize that in our new parametric equations. Importantly here is the statement is that, and again I said, given a context, there might be different reasons for what to choose, especially for x of t. But I could choose really anything as long as what I choose as the expression for x doesn't change the domain. Now again, in this case, when I'm seeing this without a domain restriction, I'm expecting that since this is a quadratic, it's a polynomial, it has no domain restrictions. It's all real numbers from negative infinity to infinity. So as long as I define x of t to be an expression that has that same domain, I shouldn't have any issues. So for instance, I could do something like define x of t to be t cubed plus 9. And then in the same vein as what I did right there, so I've described x in terms of this expression right here, this cubic. All I would need to do is take this expression and replace the x value with this expression right there. So y of t then would be 2 times t cubed plus 9 squared minus 5. And then this at this point is actually two parametric equations that work. Just because this is a square and it's not too much work, I am a bit compelled to expand this and clean this up a little bit. This isn't really a huge deal, but just I'm feeling kind of anal and I want to do it. When I multiply this out, I'll get t to the 6 plus 18t cubed plus 81 minus 5. Distribute a 2 through here, and then make sure I take care of that minus 5 with the constant here to give me y of t equals 2t to the 6 plus 36t cubed. This gives me 162 minus 5 is a positive 157. And so again, this example is just setting up for when in the near future you might have a reason to parameterize a curve. Again, one of the reasons might be is that you want to give a certain direction. These x values change a bit in terms of t. This would change faster because your t value is cubed. But there could be an example not just to kind of speed up time or whatever this parameter value is, but maybe you want to go a certain way along the curve. You can use the trick of parameterization in order to do that.